We continue to review in course algebra. First, we have the vertical symptoms. For vertical symptoms, we need to find these two things. First is make sure that the denominator equal to 0. So I say the bottom equal to 0. But we make sure that the top is not equal to 0. Because if both of them equal to 0, we will have a hole instead of the vertical symptom. Right. So first, we let bottom equal to 0. So we just have x and x minus 1 equal to 0. And we show for x, so pretty much x equal to 0 or x minus 1 equal to 0. So have x equal to 1. So have x equal to 0 and x equal to 1. So that's the first part of the problem. Next, we need to make sure that the top is not equal to 0. So we found those 2 points. All we do is just put those numbers onto the top. So we say when x equal to 0, we're going to put 0 on the top and for x. And that is 1. It's not equal to 0, which is good. So we have 1 vertical symptoms. And when x equal to 1, put 1 in for x on the top. And that is 2, which is not equal to 0 as well. So which is also good. So in this problem we have 2 vertical symptoms, x equal to 0 and x equal to 1. Alright, once again, the vertical symptom is the bottom equal to 0. We set the bottom equal to 0, but the top is not equal to 0. That's what we have. Right. That's the first one. Next, we do the same thing. We let the bottom equal to 0 or the denominator equal to 0. We have x squared minus 16 equal to 0. Now just move the 16 on the other side. So add 16 on both sides. We have x squared equal to 16. And then take the square root on both sides. Make sure that when we do that, there's a plus or minus. Right. So there'll be plus or minus square root. So I have x equal to plus or minus square root of 16, which is plus or minus 4. Right. Don't forget there's a plus or minus. Right. Then we will check when x equal to 4, the top equal to, put 4 in for x, and that is 8, which is not equal to 0, which is good. And then we check for negative 4. So the top is negative 4 plus 4 equal to 0. If it is equal to 0, that is not a vertical symptom. It's just a hole, meaning the graph will miss 1 point at x equal to 4, x equal to negative 4. So on this problem, we only have 1 vertical symptom of x equal to 4. Once again, to find a vertical symptom, that's what we need. Next we have the slant asymptote. For the slant asymptote, we will divide the top, the numerator to the denominator. Pretty much we need to have these two things. First, the degree on top should be one more than the bottom. So degree on the top equal to the degree at the bottom. Plus 1. And we require when we divide them, the remainder is not equal to 0. When these two are checked, y equal to the quotient is the slant asymptote. So for the slant asymptote, we need to check these two things. Right. So first, obviously degree on top is 2, degree bottom is 1, and so the first one checked. I'm not gonna put in the check mark on that. So first is degree on top equal to the degree at the bottom plus 1. So degree on top is 1, 2, degree bottom is 1, and that's certainly true. So yes, so that check. Next, make sure that the remainder is not equal to 0. So in that case, we just have to divide, and we use synthetic division. We divide by x minus 4. Synthetic division is by x minus c. Meaning that c is equal to 4. That means we're going to put 4 in the corner for synthetic division. Which is not equal to 0. I mean the remainder, the last number, is not equal to 0, which is good. So when the remainder not equal to 0, actually that checked, we have y equal to the quotient is the slant asymptote. So the slant asymptote is y equal to x plus 8. Right. So that's how we find the slant asymptote. Next we have the horizontal asymptote. Horizontal asymptote, there will be 3 different scenarios. If degree on the top is less than degree at the bottom, then the horizontal asymptote is y equal to 0. If degree on top equal to degree at the bottom, then the horizontal asymptote is y equal to the ratio of leading coefficient. And if degree on the top is bigger than the bottom, there will be no horizontal asymptote. Right. So just those three scenarios. Right. So degree on top. In this case, we have degree on top is equal to 1, degree at the bottom two, and degree on top is less than degree at the bottom. So the horizontal asymptote is y equal to 0. Next, degree on top, timestamp. Degree on top is 3, degree at the bottom is 2. Now degree on top is more than the bottom. So there will be no horizontal asymptote. Right. We don't have any example where the degree are equal. I'm just going to make up one real quick. We might have like let's say the function is 2x squared plus 3, 5x squared minus 1, something like that. Degree on top is 2, the bottom is 2. So y equal to the ratio of leading coefficient 2/5. Right. So that is where we have degree on top equal to degree at the bottom, and we have the acronym. So bigger on the bottom, y will be equal to 0. Bigger on the top, there will be no horizontal asymptote. And if the exponential are equal, exponential are the same, we'll divide the coefficient. Right, so that's what we have. One more thing though, the vertical asymptote. The vertical asymptote, we have x equal to something, x equal to a constant, and the slant asymptote we have y equal to, the horizontal asymptote we have y equal to. Right, just want to note that. Next we have polynomial inequalities. I'm trying to timestamp first. Right. For polynomial inequality, we need to have a function less than or greater than or equal to 0. It's not important. Just we need to have 0 on one side. So in this case, we have f of x equal to x minus 4, x minus 7, x plus 4. Right. So we will find all the zeros for the polynomial. Which be easy. X minus 7 equal to 0. X plus 4 equal to 0. So if x equal to 7, x equal to negative 4. Right. So that is where the function equal to 0. Next, we'll build the sign chart. The sign chart on the top is going to be x, the bottom is the function x minus 7, x plus 4. Right. So when we let the function equal to 0, we found two values, 7 and negative 4. I put them in increasing order because actually it is not just a line, it is the number line. And we have negative 4, and we have 7, and those numbers divide the number line. So the whole number line divided by negative 4 and 7. Right. Next we'll choose the test point. The test point will be in between the numbers. So I will choose negative 5 here. Let's put in the parentheses to distinguish with the numbers here. I should choose 0 and I choose 8. Right. And we put those numbers into the function. Just going to use the calculator here. Right over there. Right. Y equal to x minus 7, x plus 4, just the original function. Right. And I hit second table. Right. Negative 5, it is positive. 0, it is negative. And then A, it is positive. Either we look up in the table like that, or we can just hit second, calculate the value, and whatever we enter here for x, the calculator will give us y. So negative 5, 0, and then 8. But those number has to be on this number line, I mean the x-axis here. Right. So we have the sign chart. There's another way to do that, because all of this are multiplicity of 1. So when we go passing the multiplicity of 1, the signs will change. Anyway, now we go back to our problem. In our problem, what we want is, let's find another color. We want greater than 0. So what we mean is we're going to choose on the graph where it is positive. Right. So positive we see is here. I'm sorry, that is less than 0, so it's negative. So negative is going to be in the middle here, and we do not choose 0 because this does not have the equal sign, so we're not choosing the 0. So the answer is we go from negative 4 to 7. The next one is going to be the same. We have the function is x plus 5, x plus 6. And we'll make the function equal to 0. So x plus 5, x plus 6 equal to 0. So we have x plus 5 equal to 0, x plus 6 equal to 0. Give us x equal to negative 5 and x equal to negative 6. Right. Next, the sign chart. Put those numbers on the sign chart. Also, as we said earlier, those are the number lines, so we put infinity and infinity there as well. Right, the function is x plus 5, x plus 6. I put it in the factor form so it's easier to find the zero. So negative 5 and negative 6, have to put them in decreasing order. Negative 6 first, and then negative 5. Right. Those number divide the number line in 3 sub-intervals. Right, test point. Let's choose negative 7 here. Negative 5.5 go to 0. Right. Once again, I'm going to use the calculator. Right, just put that here. X plus 5, x plus 6. Right. And here we have the number negative 5.5. So that's not quite fit on the table. So we're not going to do that because we won't be able to find negative 5.5 in here. So I hit second, calculate. Instead, we calculate the values. And negative 7, that is positive. Negative 5.5, that is negative. And then we have 0. It's positive. Right, next, going to a problem we have greater than or equal to 0, meaning that we're going to choose positive. And also we choose greater than equal to, it has the equal to, so we choose the 0 as well. So going to be positive. And we're going to choose 0 as well, so we're going to choose the point as well. So the answer will be negative infinity to negative 6, including the negative 6, and then from negative 5, including the negative 5 to infinity. Sorry, I put a calculator on the way. Once again, this one greater than or equal to 0, so we're going to choose positive, and we're going to choose 0. And so positive on the outside, and 0 will be the points. So that's what we have. Right. Next, we have the rational inequality. So almost the same, we do almost the same as before, except on the rational function, if the denominator equal to 0, it is undefined. So we'll do two things. First, the function equal to 0. That means the top is equal to 0. And we find out values. So x equal to 2. And then we let the bottom equal to 0. That's where the function is undefined. That means where the bottom equal to 0. So x equal to negative 5. So we find where the function equal to 0, where the function does not exist. And then after that, it can only be positive or negative. Again, 4 scenarios. 0, undefined, positive, or negative. Once we found those two, that is 0 or does not exist, or undefined, the only two possibilities left are positive and negative. Therefore, we can put on the sign chart. X minus 2, x plus 5. Right. So the top equal to 0. Is when x equal to 2 and x equal to negative 5. Once again, the order doesn't matter. We just need to put them in. The order does matter. The scale does not matter. So we just need to put them in the right order. Like negative 2, negative 5, and then 2. Right, next. When x equal to 2, that's where the top is 0. So I'm going to make the function equal to 0 when x equal to 2. So put 0 there as well. And when x equal to negative 5, it is undefined. So in this case, we have to distinguish where it is equal to 0 and where it's undefined. Where the top equal to 0, where the bottom is equal to 0. Okay. So we have the table divided by negative 5 and 2. Right. Test point. We'll test them. Negative 6, 0, and then 3. Right? So, function x minus 2 divided by x plus 5. Right? Second, calculate value. When we have negative 6, that is positive. And when we have negative 0, that is negative. And when we have 3, it is positive. Actually, we don't need to do all of this. All we need to do is one of this. And then again, multiplicity of 1. So when we jump across the divided line, the sign will change. So positive, negative, and positive, because multiplicity of 1. Right. Next, the answer. We want anything that is positive because it's greater than 0. So we're going to choose wherever the positive sign is. So we have this and this. We're not going to choose 0 because we don't have the equal sign. And we never choose where the function is undefined. So pretty much the answer from negative infinity to 0, not including 0. I'm sorry, not 0, that's negative 5. Once again, negative infinity to negative 5, not including the negative 5, and from 2 to infinity. Right, that was that. So for rational inequality, we need to find where the function equal to 0, the top 0, where the function is undefined, the bottom equal to 0. Now, same thing here. Right, first we have the function. As always, we need to have 0 on the right hand side. X minus 1, 3 minus x over x minus 2 squared. Right. So first, we let the function equal to 0. That means the top is 0. So if x minus 1 is 0, 3 minus x is 0, so x equal to 1 and x equal to 3. Right. Next, the function is undefined. Meaning the bottom is equal to 0. So x minus 2 squared equal to 0. X equal to 2. Right. Now on this one, we're not going to use a calculator. What we use is use the multiplicity. Notice that multiplicity of 2 here. On the other points, multiplicity of 1. Right. Make a table. So we have the points 1, 2, and 3. Just need to put them in the right order. The scale doesn't really matter. Right. When x equal to 1, the top is equal to 0, the function is equal to 0. X equal to 3, the function equal to 0, the top equal to 0. When x equal to 2, it is undefined. Right. So I have that information. Those numbers divide the number line into 4 sub-intervals. So we're going to do the test point. Right. Like I said, on this one, we use the multiplicity. If we have to test where the 0 at, the 0 of course is going to be between negative infinity and 1. So we know that's going to be 0. Right. Now we just evaluate the function at 0, or finding the y-intercept. 0 minus 1, 3 minus 0, over 0 minus 2 squared. So 0 minus 1, 3 minus 0, 3, over minus 2 squared. So negative, 3 negative signs, so we end up being negative. So it is negative. Right, next. Let's pay attention on the multiplicity. This is multiplicity of 2 when x equal to 2. Everything else multiplicity of 1. Right, once again, if we go through the multiplicity of 1, the sign will change. And if we go across, I should not say across, if we're passing the multiplicity of 2, the sign will not change, because multiplicity of 2, it touches the x-axis and then turn around, so they should have the same sign. And then when we're passing the multiplicity of 1, the sign will change. Right. Next we choose the answer. Less than or equal to 0, meaning we choose the negative on the side chart. And we have the equal sign, so also choose 0, negative, that side and that side. We're going to choose 0, which is x equal to 1, x equal to 3, we cannot choose where the function is undefined. Right, so that is our answer. So we say x from negative infinity to 1, including the 1, or from 3 to infinity. Right, so that's what we have. Next we have compound interest problem. Right, so there are two formulas. This one is compound interest, where n is the number of compounding period. If it is compounded continuously, we're going to use this formula. Right, so first, let's read the problem. Find the accumulated values, so that is the future values. So I'm just going to say they ask for the A investment of 5,000. So originally we have 5,000, that's the principal. 5%, that obviously the rate. Let's write that. We must write that as a decimal. And compounded monthly. Monthly is n equal to 12. 12 times a year, that is. And for 8 years, that means t is equal to 8. Right, so pretty much we have everything but the future values, accumulated values. So A equal to P 1 plus R over N over NT. This one is compounded monthly, so we're not going to use the continuously compound interest. So we have 5,000. 1 plus 0.05 divided by 12, the power of 12 times 8. Right, I'll just put everything on a calculator. Right, 5,000 times 1 plus 0.05 divided by 12. So that is compounded monthly. If it is compounded continuously, we're going to use, need to put the calculator away for a moment. If it is compounded continuously, we're going to use A equal to PE R to the T. If it is compounded not continuously, then we're going to use that formula, right? Now investment of 3,000. That's the principal. Accumulated value, that is the future values, which we don't know because we asked to find it. 7%, that's the rate in decimal for 6 years. T equal to 6. Pretty much we have everything. We'll just put in the formula 3,000. E R is 0.07. T is 6. $3,000. Second, the LN key. $0.07 times 6, 4,000. 565.88. Right, so that's all we do. Right. Next, we'll convert between exponential form and logarithmic form. So exponential form or the logarithmic form, we always need to find the base of the form. The base in the log is in the subscript. The base on the exponent is on the same level as what we write. So this is in logarithmic form. We're going to write that in exponential form, meaning that we're going to need the base, which is b, equal sign, and after that we just swap the other two numbers. So 3 and then 64. Right, so that exponential form. Logarithmic form is also required to know what is the base. The base is here 3, so we have log base 3. We're going to keep that on the same sign as the original problem, and then we swap the other two. (1/27) here, and then the -3 on the other side. So that's all we do there. So the next problems, I should say the next 5, we just evaluate this without the calculator. So I'm going to do 2 different ways. First, the less obvious way, I should say the common sense, so it should be the obvious way. Make that equal to x, and then we solve for x. So we switch to exponential form. 12 is the base, equal to x goes there, and square root of 12 goes to the other side. Next, we use these properties. If we have a radical m on the top and on the index of radical, index of the root, so we're going to have b over m over n. So that we have 12 to the 1/2. So 12 to the x power equal to 12 to the 1/2. Obviously x, these two are equal, the bases are equal, so x equal to 1/2. The exponent must be the same, so that's what we have. Right, I said that is the common sense. We just don't have to do much. All we can do doing this way will require knowing the properties. First we write square root of 12 again is 12 to the 1/2 power. When we have that, we can simplify. Log base 12 and 12 cancel out, left us with 1/2. So when we have the log and exponential composed together, they will cancel out. Right, so we can do it either way. Next, again, we don't know what it is. We can always make that equal to x, and then we swap. 2 is the base to the x power equal to 1/4. Now 1/4 is 1/2 square. Now the 2 square from the bottom move to the top, it becomes negative. So let me write the formula here. 1/b to the m is equal to b to the negative m. So cross the line, change the sign. So from here we have x equal to negative 2. Because two things are equal, the bases are equal, then the exponents must be equal. Right, so that's one way to do it. Another way to do this is we use the properties of the log base 2 of 1/4. 1/4, we're going to write 2 to negative 2. Now the bases are the same, so the log and the exponential in composition of each other, so they just cancel out, give us negative 2. Like that, either way works. Next, also do that in two different ways. We make that equal to x, and then we swap 7 to the x power equal to. Now, notice that the difference of these two, this is in exponential form. So 7 to the x power, we're not going to write like that. This is already in exponential form. So we're going to change this to logarithmic form, where the base is still 7. And of course, we're going to swap x and log base 7 of 11. Swap those two. X goes here, and then log base 7 of 11. Obviously, from here, x is equal to 11. Or we could do that directly. 7 log base 7 of 11. Once again, just like that, like this too. If we have the log and exponential function composed, the function, the log and exponential function composed between each other, then and they have the same base, so they just cancel out. So we're going to have 11. Right. Next, I'm not going to make this equal to x and then do that. I'm just going to use the properties of the log here. So log, we can write this as log base 10, because by default, the common log don't need to write the base 10. 1 over 10,000, I could write 1 over 10 cubed. And then cross the line, change the sign, move that up. We have that. And then the log and exponential function of the same base, when they combine or when they compose together, that just give us negative 3. Right. And next one, ln is the log base e, and e to the 7 at bottom move to the top. And then we have the log exponential function of the same base, cancel out, so we have 7. Next, just have the domain of logarithmic function. So all we need is this. Doesn't matter what the base is, whatever we put into the log, or we call the argument of the log, must be positive. If it's negative, it will be undefined. So what we do is we let x plus 6 greater than 0. And now we solve for x greater than -6. So it will be greater than -6. And don't have the equal sign. So we write from -6 to infinity. Right. Next we will use the properties of the log to expand or to condense the log. So I will write the properties that we need. Doesn't matter what the base is. Log of a product is the sum of the logs. Log of a quotient is a difference of the logs. And if we have log of a power, we can take the power outside as a coefficient. Right. Once again, multiply, turn to a plus, divide, we subtract. Now, and besides, we should also write this. If it is positive coefficient, it will stay on top. If it's negative, it will be at the bottom. So write positive is for the top and negative for bottom. Right. So those are the properties that we have. So first we have two factor x squared and y to the 7. The x squared on top, so it will be positive. The y to the 7 at the bottom, the base 2 though. Y to the 7 will be at the bottom, will be negative, I mean. So on top positive, bottom negative. And finally, just need to take the exponents outside. So we have 2 log base 2 of x minus 7 log base 2 of y. So that's the first one. Right, on this one we have x and then times y to the 7 and then divide by z squared. So we have 3 terms. The x on top, y to 7 on the top, z squared at the bottom. Whatever on top is positive coefficient. And then also plus log base b of y to the 7. And then z squared at the bottom will be negative log base b of z squared. And then we take all the coefficients outside. So we have log base b of x, 7 log base b of y minus 2 log base b of z. Right, so that's all. So this is called expanding logarithms, meaning we have one big log, we expand them into a bunch of little logs. So remember, when we're expanding or combine we have to have one of each log. So on the next one, we need to do that first. We take the b, the 3 inside, because the goal is to have one for each log. Right, and this is subtract, and so positive, whatever positive will stay on top, negative will be at the bottom. So just going to write like that. Next, also need to do that. Take the 2 inside and the exponent inside, because we must have one for each log. So 1 log of x squared and 1 log y to the 1/4. And then there will be a log, just ln, positive coefficient, so x squared on the top and y to the 1/4 at the bottom. And finally, we could write y to the 1/4 as the 4th root of y. Alright, so that's what we have. Next we have exponential equation. So this one is when we have the same base. So either we have the same base, then we do that, will be easy. If we don't have the same base, we will take the ln on both sides. Right, now (27) is 3 cubed. So write like that. Now 2 numbers are equal, the bases are equal, so the exponent must be the same. 1 plus 2x must be equal to 3. So we match the exponents. Bases are the same, exponents must be the same. Right, subtract 1 on both sides. 2x equal to 2, where we subtract 1 on both sides, and then divide by 2, so x equal to 1. So that's what we have. So for exponential equation, we don't need to check the answer, because domain of exponential function is all real numbers. Right, more of exponential equation. Right, so we have 2 to the 3x plus 7. 1/4, we can write 1 over 2 square, move to the top, becomes 2 to negative 2. Right, now exponential equation with the same basis, then the exponents must be the same. 3x plus 7 equal to negative 2, and then we'll just solve for x. This will be very easy. My 7. So 3x equal to negative 9, divided by 3, x equal to negative 3. So that's all we do there. Next we have this equation. 4 base 4 and then 7. There's no way we can change them to the same base. We could swap this to exponential form, or we are going to take ln on both sides. So taking ln on both sides here. When we do that, we can take the exponent outside. That's the whole reason why we take ln on both sides, or any log for that matter. We still have ln of 4 and then ln of 7. Now we just need to solve for x. To do that, we can divide by ln of 4. So if x plus 8 equal to ln of 7 over ln of 4. And then we just subtract 8 on both sides. We have x equal to ln of 7, ln of 4 minus 8. So that's what we do. Right. I also want to do that differently. 4 to the x plus 8 equal to 7. We could swap to exponential form. Swap to logarithmic form. Base 4. So we say log base 4. And then we swap the 7 here. And the x plus 8 there. And minus 8 on both sides. So we have x equal to log base 4 of 7 minus 8. For this one, we can rewrite as using the chain of bases ln of 7 over ln of 4 minus 8. Of course, they must be the same. So, if the exponential equation have the same basis, then the exponents will be the same. If we cannot turn them into expression with equal base, then we have to take ln on both sides, or we swap to logarithmic form. Right. Next we'll go to logarithmic equation. For logarithmic equation, we have to check the answer. Because the domain of logarithmic function is all positive, so we cannot put negative inside the log. But the first one is very simple. We have log equal to number. Just look at on the base scheme. On the bigger scheme, classified logarithmic equation. On this one, we have the log of something equal to number. So on those two, we have the numbers. On this one, we have all the logs. Right. So when we have a number, then we have to write that as the log equal to a number. And after that, we swap base 2. Base is 3. Swap the 2 on this side, and x plus 1 on that side. So 9 equal to x plus 1. So x equal to minus 1 on both sides. X equal to 8. Right. I should not do that yet, because I need to check. When x equal to 8, log base 3, 8 plus 1 equal to 2. So put 1 in for x. Whatever inside the log or all the argument must be positive. So yes, that's good. And it did. X equal to 8. Right. Next, we also do similar thing. However, we have 2 logs instead of 1. But we can combine them. So let me write the timestamp first. So we combine the logs here into one big log. It is a plus. So we write that as a product. Base 4, x plus 5 times x minus 1. Equal to 2. Now we swap. Base 4, swap the 2 over. And then we have x plus 5 and x minus 1. Swap to the other side. 4 square 16. Right, I will multiply this out and put on the left hand side x squared minus x plus 5x minus 5. 4 squared 16, put on the other side. Combine like terms and move everything on the left hand side. 16. We have x squared plus 4x minus 21 equal to 0. Right. Here we can factor completion square or use quadratic formula. I just use quadratic formula. Negative b plus or minus square root of b squared minus 4ac over 2a. Negative 4 plus or minus square root of 4 squared minus 4ac over 2a. So negative 4 plus or minus 4 squared 16, and then we have 4 times 21, so that 84 and 16, that square root of 100 over 2. So if x equal to negative 4 plus or minus square root of 100 is 10 over 2. So we have x equal to minus 4 plus 10 divided by 2. So that's 6 over 2 is 3. And then x equal to minus 4 minus 10 divided by 2 minus 14 divided by 2 is minus 7. Right. So we have that. Need to check the answer though. So let's just write x equal to 3, x equal to negative 7. Now we check. When x equal to 3, I put 3 in for all the logs, for all the x in the log. X equal to 3, x equal to 3. So inside this log, that is positive, which is good, and that is also positive, which is good. So that is good. Now when x equal to negative 7, log base 4 of put negative 7 in for x, and we don't need to write the rest of the problem because we have a negative inside the log, which is no good. Right. So for logarithmic equations, always have to check the answer because whatever we put into the log, the argument of the logs must be positive. Right. This one's different. We don't need to swap to exponential form like this because we have logs everywhere. Right. So we have logs. By the way, this is base 10, the common log. We can combine these two together. The sum turn into a product. Now both of them base 10, log base 10, then we just make them equal. So multiply it out for x minus 4, move the 4x over. So we have negative x equal to negative 4, so x equal to 4. Now just need to make sure that all the arguments of all the logs are positive. So put 4 in for x. Put 4 in for x. All of them are positive. Yeah. So this is the good answer. Because when x equal to 4, all the arguments of all the logs are positive. So we have that. X equal to 4, which is good. Right. Next we have two application problem. One is compound interest, continuously compound interest. And then the other one is half-life. Right. So how long will it take? 300 $3,000 to earn $500 interest. And then they said we use this formula. Right, how long does it take $3,000 investment? So initially we have 3,000. And then earn 500 interest, meaning that the future values we have 3,000 initially, and then 500 in interest, 3,500. Invest is 8%, so that obviously is the rate in decimal, compounded continuously. That's why we use that formula. Right. So A equal to PERT. So we have 3,500 equal to 3,000 e to the 0.08 t. We don't know t. Now we just need to solve for t. First, we're gonna divide by 3,000 because we try to get the exponential term by itself. So let's divide by 3,000. So cancel the two zeros. We have 35 over 30 equal to a 0.08 t. Now we solve for the exponential. The variable in the exponent. So they don't have the same base. So we'll take ln on both sides. The reason of that is we can take the ln, the exponent outside. So I have ln of 35 over 30 equal to 0.08 t ln of e. Now ln of e, if we write that ln of e log base e of e to the first, those cancel. So ln of e is equal to 1. So meaning that 0.08 t equal to ln of 35 over 30, and then divide by 0.08. So do that. Now we bring back the calculator. ln of 35 over 30 divided by 0.08. We have 1.92. Let's round that to 1.93 or 1.9 years. Right. So, and this one we would solve for the variable on the exponent. So exponential equations. So try to get the exponential term by itself, and then check ln on both sides if they don't have the same basis. Right, last one on this review. Right, the half-life. So most of the half-life problem, it will be in two parts. So I'm going to divide this in two. The first part is the half-life is equal to 710 years. So first the formula. The formula we can use the compound interest formula, or we use, let's say, a little bit. Say the amount is equal to original amount e to the RT. Right. So we just change a little bit initial amount with time t. Right. Now first part, the half-life of silicon 32 is 710 years. So what does that mean? meaning that if initially we have A naught, and then half-life meaning we have half of it, and it will happen after 710 years. And so let's put all of that in the formula. 0.5 A naught equal to A naught e to the, we don't know R, but we know the rate. Know the time is 710 years. Right, so obviously from here we have everything else except for the rate. So we're looking for the rate. First, divide by 0.5 on both sides. I'm sorry, we don't do that. Divide by A naught on both sides. A0. Sorry, divide by A0 on both sides to cancel the A0. So we have 0.5 equal to e to the 710 R. Next, we'll take the ln on both sides, because solving for the variable on the exponents, and when the base are not equal to, we're going to take ln on both sides. And just like the last problem, ln of e is 1, so pretty much cancel out. But we'll take the exponent down first. ln 0.5 equal to 710 R. ln of e returns to 1. And finally divide by 710. We have R equal to ln of 0.5 divided by 710. Calculator. ln of 0.5 divided by 710. So that is very small number. I try to write this as a decimal. Let's see if I can do that. Right. Nope. Let's say if instead of normal, let's give this as not scientific, not engineering. So let's just write that number first. Negative 9 times 7626. The e meaning times 10 to the negative 4, meaning that we move the decimal places 4 points to the left, so negative 0 point. So do that. Right, let me just write that on the next part of the page. So R equal to negative 9.7626 times 10 to negative 4. Right. So it's going to be negative. Now move the decimal places. 1, 2, 3, and 4. Again, if we want to write like this, we move decimal places 1, 2, 3, and 4. So that to the negative 4. So decimal is right here. By the way, just give the scientific notation numbers. Right. So that's the first part of the problem. First part of the problem is to use the half-life to find the rate. So the half-life gives us the rate. This is half-life. Next, how much will be present in 300 years? if original we have 30 grams, so originally we have 30, how much will be there after 300 years? So what is the amount after 300 years? We already have the rate, which is good. So put in everything we know in the formula. We don't know A. We know A naught is 30, E, and the negative at the rate is going to be that number, 9.7626, and then T 300 years. That time 10 to the negative 4 times 300. Right. So calculator. So we can just keep that number. Originally we start with 30, and then E, that will be second, and ln. Right. We just go up there, hit enter. So like copy and paste. So when we highlight something, hit enter, it will paste right next to what we have. Alright, let's put the parentheses around this. Let's do that again. Parentheses up there, copy and paste, and then times 300. So we have 22. 3 decimal places, 22.383. Originally grams, so this also grams. Right. So again, the half-life will be 2 parts. Usually, we use the half-life to find the rate. That's the first part. The second part is we just have to put in this formula. Depends on the question asked. We could ask to find initial, the final amount, R or T. We cannot or T because we found R already. Right. So the first part is using the half-life to find the rate. After that, we have to find what is missing from that equation for the second part of the problem. Right. So I'll stop the review here, and then we'll continue next time. I hope you find this helpful. Thank you for watching.